All right, so now we're going to talk a little bit about the asymptotic theory of hypothesis testing. So previously we had been talking about how estimators converge in some appropriate sense as you get more data, and so we're going to apply those ideas now to hypothesis testing. Okay, so um, so let's see what happens when the number of observations is large. So we consider the case where the number of observations is large. In the context of hypothesis testing. Okay, so so basically what you want to do, for example, is to test some sort of null hypothesis. So you want to test a null hypothesis. Say the null hypothesis is that u is equal to some nominal value u0 against sort of an alternative. Hypothesis say that u is actually greater than u0. Okay, so this is just a one-sided test. It's more generally, it's like you might, it's like just care about whether or not it's equal or not equal. But just for the interest of illustrating this idea, let's just look at this one-sided test. Okay. So, and we want to do this in an exponential family. Say a one-dimensional exponential family, which is curved. This is a set of probability distributions. It's like where there's a parameter theta, which depends parametrically on u. Okay, so this is a one-sided test. Because we're just looking at this inequality, right, where u is greater than u0. But you can generalize this to sort of two-sided tests as well. Okay. So, all right. So what's happening now is that we're going to assume that, again, S is a curved exponential family. So the basic idea then is that we want to construct a rejection region, right? So S is a curved, well, it's actually a curve in some embedding manifold that's like of exponential families, right? And we can design a test by basically defining a rejection region R in M, okay, such that the hypothesis H0 is rejected. If the observed point eta bar, right, is in R. And the hypothesis is accepted. Otherwise, okay. Right. So, it's like this is sort of fairly similar. It's like to what you have. It's like if you had, for example, a some sort of estimator, it's like which is distributed in some sort of probabilistic fashion, say a Gaussian. It's like, and you want to figure out, it's like you want to construct basically an acceptance region, right? Which it's like where if the true value it's like was U0, it's like that, it's like if there would be a very high probability, it's like that the sort of observed point would be in the rejection region. Well, actually, it would be in the complemented rejection region. It's like if the null hypothesis is satisfied, right? Okay. So let's see. All right. So clearly, it's like if you want to have a situation where the hypothesis is accepted, it's like if you're in outside, it's like the rejection region, then clearly the rejection region shouldn't contain U0, right? So the rejection should not contain U0. Right, again, the null hypothesis H0 is that U is equal to U0. And then the alternative hypothesis is that U is greater than U0. Okay, so this rejection region R should not contain U0. But there's a sense that its boundary should lie close to U0, especially as n tends to infinity. Right. So B, which is the boundary of the rejection region, right, should be close to U0, right, as n tends to infinity. Right. And, it's like the reason, of course, it's like why that should be the case is that as n goes towards infinity, then the observed point is the distribution, it's like which you have for the observed point, it's like will tend to be concentrated about its true value. Okay. So as n goes to 0, the likelihood that if you are far away, if the observed value is far away from U0, the likelihood that the actual value is U0 becomes smaller and smaller because of this concentration of the measure about U0. Okay, so this is the reason why we have this condition that you want the boundary of the rejection region should be to get closer and closer to U0 as the number of samples as that goes to infinity. And I guess implicit in that is this idea that it's like you're constructing the test based on a consistent estimator, if you will, right? Because otherwise, it's like you won't have that kind of concentration. Consistent, unbiased estimator, for example. All right. So let's see now. All right. So the boundary surface, let's call that B, depending on U0, right? of R, right, depends on the null hypothesis. U0. Okay, and we denote that dependence by the fact that B is, you know, a function of U0 in some sense. So it is a n minus 1 dimensional hypersurface right, which crosses this set S, it's like, which is this one-dimensional curved exponential family, okay, at a point. Let's call that U0 prime, okay, which converges to U0, right, as n goes to infinity, right? So this is just another way of basically encoding the same condition which we wanted, which is to say that the rejection region should get, you know, it's like closer and closer, it's like to the null hypothesis as n goes to infinity. And again, because as n goes to infinity, it's like your estimate of what the, you know, it's like the parameter is gets better and better, all right? And so if you actually get an estimate which is far away from the value, the null hypothesis, then there's a very high likelihood, especially when n is very large, right, that the null hypothesis is not satisfied and you should reject it, okay? And so let's call that boundary n. Okay, so let the boundary of the rejection region as a function of n right be denoted by an u0. Okay, so so there's this one parameter family of u's. It's like right, which is modeling this space of statistical models, right? This is embedded in some ambient space M. So this is S is this embedded curved family of exponential distributions, right? And then there's a some sort of exclusion region. Okay, so this region here is R. And then there's this U0 prime. And this set here is well, okay. So you should, yeah, so you have some sort of rejection region. It's like, and then this is the boundary. Well, I mean, this piece here is the boundary. I'm not sure how to express this. But you should think of this as maybe like a surface, right? And then this is a solid piece, which is the rejection region. And so this is an U0, right, which is the boundary of this rejection region. Okay. Okay. So you let u equals to u0, right, be a free scalar parameter. Because you're sort of assuming S is just a one-dimensional curve, right? Then you form the ancillary family. Of A, right? So this is the stuff it's like which we saw before. It's like when we're talking about sort of estimators, it's like for curved exponential families, right? The idea is that you have these curves are going to give you essentially a foliation, right? And the foliation is then going to define essentially a rejection, projection, basically. And this depends on n, right? Which is the number of samples. So so as before, it's like this ancillary family. It's like gives you a foliation. So this gives foliation of m, consisting of the boundaries of the rejection regions. For various hypotheses, for various null hypotheses. Okay. So you can then use this. It's like to analyze. It's like the performance of hypothesis testing. So you can use this to analyze the performance of hypothesis testing. So let me state a theorem. Right. So the basic idea is simple. So so you know that so the first order asymptotic theory is easy because basically you know that this sort of observation, it's like which you construct, right, using some sort of estimator converges, it's like to the true value as if the null hypothesis is satisfied, right? Okay, so this sort of estimator, right, converges to the dual coordinate associated with this null hypothesis value under the null hypothesis. Okay, so what that basically means is that if it was indeed true that the null hypothesis was satisfied, which is that u is equal to u0, then it's like this estimator which you construct, it's like from the observed data, is going to converge to the dual coordinate associated with that value u0, right? That's sort of just saying, that's just a consequence of the fact that, you know, it's like this estimator which you constructed is sort of asymptotically unbiased, right? So, and consistent as well. So the theorem then, well, yeah, so actually that's a consequence of the estimator being consistent. Okay, so a test is first order efficient. Right, when the associated ancillary surfaces an of u, right, passing through un is orthogonal to S, and un converges to u0 as n tends to infinity. Okay, right. So so again, you're basically using, in some sense, it's like what you're basically saying is that the test is first order efficient if the way you set up these ancillary surfaces are so that the it's like the estimator is first order efficient, right? So if you recall, it's like this condition that the ancillary surfaces are orthogonal. It's like to the it's like this submanifold of curved exponential families, right? That condition that it's orthogonal is the necessary condition. It's like for your estimator to be first order efficient. And so more or less, it's like if you construct it's like the test in such a way that it's compatible with that condition, then you could have a first order efficient hypothesis testing as well. Okay. All right. So so there are many, it's like sort of first order efficient tests, right? And then so the problem is that if you look at higher order efficiency, then or if you look at higher order, it's like asymptotic theory, then there isn't as uniform a theory it's like one can develop for this. And it really depends on the problem. It's like which one is going to be better when you're looking at its higher order properties. Okay, so let me just stop here for now.